Okay, I need to record it for the students, so I think I have it down. I can record it on Zoom as well. Okay, great. Okay, so welcome to this session. Again, this is the first live session for the class Digital Logic. Again, the aim of having this live session is just an opportunity to speak with students, to clear up any problems that they're having, to clear up any questions that they may have. And I'm hoping that this interaction will enhance the class experience in learning about digital logic circuits and applications. As I mentioned sometime earlier with Yontre, this course is one of the easiest classes in the program, and so the emphasis is not just on learning digital logic principles, but the emphasis is also on learning some other soft skills. Number one of the things that we focus on is practice. So you have lots of examples to practice with digital circuits, to practice with building circuits, to practice with also using LEDs, using switches, using digital logic devices, using also the data sheets from these devices as well. So again, you have lots of opportunity to practice. You also have opportunity to practice design. That is where you are giving specifications and you go ahead and build a circuit, or you design a circuit that will actually achieve the desired logic, right? And again, these circuits are not very complex. You're able to test them. You're able to troubleshoot if things are not working as they're supposed to. And so today, I'm going to sort of just give a brief overview of the topic, go into some of the concepts that were introduced in chapters 1 and 2, and also run through some of the logic gates and the concepts that are introduced in chapters 3 and 4 as well. Can you guys still hear me okay? Good, thank you. Okay, so let's start with digital logic by itself, right? Quick definition. When you think of digital logic, just the words in the title of the course tell you that we are dealing with digital and logic. Now, if we define digital, we come to a concept of using digits, right? The exact opposite of digital would be analog. And in analog systems, we have continuous variables. For example, we look at temperature. The temperature is a constant variable. At every time there is a temperature, right? If you go every millisecond, there will still be a temperature because it's a continuous variable. When we deal with digital systems, we are dealing with systems that are sampled, right? We sample a continuous variable, and we have a value for that variable for regular intervals, right? So for example, if you wanted to record the temperature, you would sample the temperature probably every second, every millisecond, and whatnot, and you would have that information for just that period of time, right? So digital information talks about sampled information. This is where we sample a continuous variable. Now, after we sample that variable, we need a way to represent the information, right? Now, for example, if you look at temperature again, we have a scale of temperature. And so we actually have some digits that represent the temperature. If we wanted to represent the temperature that we sampled, we would need to write it down. And of course, we use the decimal number system, so probably we'll write it down in decimal, where we have one digit. The first digit represents the ones, and the second digit represents the zeros. So digital logic, in a sense, we are using digits, but we are focusing on a particular number system, which is the binary number system. Now, this binary number system is very popularly used in digital systems. And when you think of digital systems, you think of computers or any systems that is able to store data, right? And so I'll share a little bit on it in a second, right? So again, when you think of digital, you think of using sample data, right? Of course, you represent this data using numbers, right? And again, primarily, the way we want to represent the sample data is using not just any number system like decimal that we use, but we probably want to use binary. And the reason why we like binary is because we can represent binary using voltage levels, right? We can represent binary using 2 voltage levels, right? We can, for example, if we in binary we only have 2 digits, which is 0 and 1, and we can represent the 0 using 0 volts. We can represent the 1 using like 5 volts or any number that we choose, right? That makes it easy for us to design circuits because our circuits are not very complex now, right? Our circuits essentially have only 2 states. Either they're going to be on or they're going to be off. And so using binary, we only, like I said, our circuits are going to be much simpler. We only design circuits that operate as switches. Either they're on or off, to represent a 1 or 0 for a particular amount of time. And yeah, and again, we have devices that are active, right? So when they're turned on, when they're powered, the output is high, and when you remove the power from them, then the output goes back to low. We also have some devices that behave like capacitors. So when we turn them on, right, the output goes high, and pretty much after you move the power, the output stays the same. So in this course, we will look at a number of different devices. The first set we're going to look at is gates, logic gates. Then we want to look at, okay, well, what can we build with the gates, right? There are other devices that we can build with the gates, such as encoders, decoders, arithmetic logic units, adders, subtractors, and so forth. We also have, when you think of digital systems, you think of calculators, you think of microprocessors. All of these are complex digital circuits, but the basic building block of these are going to be digital logic gates, right? And so it's good for us to get a good understanding of the binary number system and how data is represented using that system. Like I said, because it's easy for us to design circuits that operate with only 2 voltage levels, and we can use that to represent information. All right. Now, again, this is just talking about digital. Now, what about logic? Of course, when we think of logic, we think of something that a methodical way of representing a condition based on inputs and outputs, right? For me, when I think of logic, I think of the truth, right? You think of what should happen based on a particular set of rules. And that is exactly what happens with digital logic circuits, right? We have a set of rules that governs the behavior of a device, right? And so seeing that, we can then predict what the output of the device should be based on this set of rules. For example, if you look at the gate, all right, the logic gates, all of them have a particular set of rules that govern the behavior, and based on that, we can determine if you change certain inputs, what the output should be based on the logic of that particular device. Now, if you think of a microprocessor, there are rules that govern how the microprocessor should operate, right? That is how we're able to program it to do X and Y, because we know the logic that essentially governs its operation, right? So again, when you think of digital logic, think of sampling a continuous variable, right? You think of data that is sampled. So we want to represent that data in a particular form. And of course, we're going to use digits to represent that data. And then we're saying we don't want to just use any digits. Probably want to use the binary number system, because in binary we only have 1s and 0s, and then that makes it easy for us as electronics engineers to design circuits that have only 2 states, right? So again, if you think of your computers, you think of any modern electronics, use digital circuits inside. And so what we are studying in this course is essentially the building blocks of all digital circuits, right? All right. So let me give you a quick example that just shows you how we can use digital systems, right? So I'm going to give you an example where we sample a continuous variable and how we represent that using information. So I know in the class I asked you guys to essentially I gave you some work where you have to use the binary number system and so forth. So I'll go over that very quickly as well. Any questions so far? So like I said, I'm going very quickly, but if you have any questions, I will stop to help answer your question. All right, great. Okay, so I'm going to put on my other screen and just write really big on the screen here and see what we get. All right, you guys can see my piece of paper? All right. Okay, so again, the first example I want to give you of digital logic systems, we're saying that we want to represent sample data. Or sampled variable. So what is sampled? Again, if you have a graph right here, say we have the temperature, and the temperature is cyclic, so it's hotter in the day, colder in the night. That is the temperature. It's continuous, right? I'll put T here for temperature. If you want to represent that information, you can use a voltage and a transducer to show you a voltage to represent the temperature, and it's going to be continuous. But if you want to sample it, we are going to take the temperature at different points. Let's say we take it every hour, right? So we have information to represent the temperature at every hour. So you can see here we have a limited or fixed number of points, right? So this is going to be the point right here. All right. In a digital circuit, normally we will have a sensor, right? So the sensor can also be called a transducer. And of course, the transducer is a device that converts a signal from one form to the other, right? So you may have a sensor that transfers a change in temperature. It transfers it to a change in resistance or a change in voltage, right? Or a change in current. So it essentially converts a signal from a change in one signal to a change in another, right? That's what a transducer does. So you have a transducer that you are going to sample, right? You have either you have a resistance or a voltage coming here, and that normally goes to an amplifier. So you normally amplify it, and then it goes to what is called a analog to digital converter, ADC, right? Analog to digital converter. And of course, we will see this in the end of the course, but this just shows you how we use digital systems, right? So it goes to an ADC. Now the ADC takes the analog voltage, so it takes voltage and it converts that voltage into a number, right? So for each voltage that we get in the ADC, we're going to get a binary number representing. So let's say our voltage here is 2.5 volts, and let's say that the highest voltage that this ADC can convert is 5 volts. So here we can have 0. So the number we're expecting here, based on the resolution of the ADC, let's say the maximum resolution here is 1023, and we have 0 right here. We expect the ADC output to be the number. It's going to be 512, right? We expect this to be the output coming from the ADC. Now, of course, the ADC output is not given in decimal. This is decimal right here. It's going to be given in binary. So to know if we have some cables connected to this ADC, and I'm going to show it to you, most times the ADC output is in parallel. So you have one line to represent each line of information, and it goes in a buffer, right? So let's convert this 512 into binary and to see what the number will be that will come from this ADC. So again, we have 512, and if we want to convert it into binary, we can use the long division method, or we can use the expansion method. So let's do the long division method here. 25 is going to be 2, remainder 1. So I'll put the remainder right here. We have remainder 1. So it's going to be here 2 256. Sorry, 256. All right, 2 into 256, we have, is it 128? So remainder 0. And 2 into 128, 64, remainder 0. 2 into 64 is going to be 32. And all of this is going to be perfect until we get to the last one. Remainder 0. This is remainder 0. 2 into 32 is going to be 16. Remainder 0. 2 into 16 is going to be 8. Remainder 0. 2 into 8, 4. Remainder 0. 2 into 4, 2. Remainder 0. 2 into 2, 1. Sorry, 2 into 2, 0. And the remainder is 1. So if you look at our number here, we have one that represents 512, and the other one represents 256. This represents 128. Okay, hold on. Here's the answer. Okay, we start with this one. This is the most significant bit. So we have 1 here. This represents 512. 0 represents 256. 0 represents 128. 0 represents 64. 0 represents 32. 0 represents 16. 0 represents 8. 0 represents 4. 0 represents 2, and 0 represents 1. Again, like you saw in the example, this is the ones column right here. This is going to be the 2's column, 2 to the 1. This is the 4's column, 2 squared. This is the 8's column, 2 to the 3. This is the 16's column, 2 to the 4. This is the 42's column, 2 to the 5. This is the 64's column. This is the 128's column here. This is the 256 column, and this is the 512 column, right? So this is what we're going to get from our ADC, right? So this is the number of digits that we're going to get. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, based on the resolution of the ADC, now you have ADCs that are 12 bits. You have those that are 10 bits, etc., etc., right? The more bits you have, the larger number of steps you can break down the voltage into. So again, the ADC normally has a parallel output, right, to send this data into the buffer, right? So again, how is the data transmitted? We said that a high represents a 1 and a 0 represents a low, right? So there are two ways you can send data. The only way you can send data, the first way is serial. All right, and this is where you send the data one at a time. So you use a clock, and the clock tells you when to check for each data. So again, this is going to be like so this is 0, this is 1, 0, 1, 0, 0, 1, 0. So again, you have 1, 2, 3, 4, 5, 6, 7, 8 clock pulses. So you use 8 clock pulses to send this information, and most times it goes into a buffer, where it comes into the buffer and it is saved into the buffer. And again, when I say a buffer, it means that, okay, the value is not going to change, right? After you stop sending data inside of it, whatever you sent is going to remain there for a while, right? So the other way you can send data is parallel. This is where you have multiple lines connected, and this is what we said with the ADC. And so you use 1 clock cycle, right? Instead of having 8 clock cycles, you only use 1 clock cycle, and you have 8 lines, right? And of course here you're going to send here 0, and I can just draw the signal here, 0, 1, 0, 1, 0, 0, 1, and I think I'm missing one more, 0, right? So you use 1 clock cycle, and the information is saved in the buffer after 1 clock cycle, right? So again, this is how most times this is how we get digital information from the real world. We need to use a sensor or transducer. We're going to amplify that information, and then we will use the analog to digital converter that converts our analog voltage into a digital form where we have ones and zeros, right? Again, we're going to have here 1000, this number right here. So we have a binary number representing our information, right? All right, so let's go on to the next thing that we discussed. So again, in the class, we talked about converting digital numbers. So I'll just breeze through, probably just work one example here. So again, we know of the decimal number system, right? Okay, is my camera still good, or did it switch back? Okay, great. So again, we know of the decimal number system. Let's put an example here, 901. We know that, okay, this column here represents the ones column, which is the same as 10 to the 0, right? And this represents the 10 to the ones column, which is the tens. This represents the 10 squared column. So we know this is ones, we know this is tens, we know this is hundreds, right? Tens, right? We cannot, again, this is what we know. And of course, we know how it works, right? So this is 1 times 1. This is 0 times 10. This is 9 times 100, right? So this is 901. Okay, so this same principle we can apply to different number systems. And in this class, I think we introduced the octal, which is base 8. We introduced the hex, which is base 16. And of course, we introduced the binary, which is base 2. Right? And again, the same principle applies. The same math, whatever math you can do in this number system, addition, subtraction, division, squared, cube, square root, you can do the same thing in the other number systems as well, because they are real number systems, right? So again, let's look at the expansion example for hex example. So again, with the hex, we have, so I gave you already the different numbers, so I'll just write it down here. So for the decimal, we have 10 digits. We use 0 to 9, correct? So again, notice here, anytime you write a number in its base, so if you wanted to write 10 in base 10, you're going to write 10 with using 1 0. That's a very important observation, right? Because this represents 0, this represents 10. So anytime you write 10 in base 10, you're going to have 1 0. If we come down to binary, we have the numbers 0 and 1, right? So again, you see the highest number is always one less than the base. So this is base 10. The highest number is 9, one less than the base, right? To write 10 in base 10, 1 0. If you look here, the highest number for binary, which is base 2, is going to be 1 less than the base. So, all right, so this is base 2. Again, of course, this is base 10. Okay, the highest number is always 1 less than the base. So again, that highest number is going to be 2 minus 1, which will give you 1, right? If you look here, if you wanted to write 2 in base 2, it's going to be 1 0. Again, look at the observation. You want to write 2 in base 2, it's going to be 1 0. Why? Because this number here always represent the ones. This is the ones, this is the ones. This is going to be the base. So it's going to be 10 to the 1. This is going to be 2 to the 1. 2 to the 1 will give you 2. So this number here represents 2 in base 2. This represents 10 in base 10. Let's look at the octal, which is base 8. Okay, here we're going to have the numbers 0 all the way to 7. So again, 0 to the base minus 1, right? Again, to write 8 in base 8 is going to be 1 0. Okay, why is that? Because this number is always the ones, and the highest number of ones we can have is 7. When we go to 8, we need to have a 1 in the 8th column, because this is going to be 8 to the 1. So we have the 8th column here, right? So again, you notice a pattern if you go to the hex. Again, for hex, we need to go, hex is base 16. And of course, we are going to go 0 to 15, right? But of course, if you write 15 like this, it's going to have 2 digits. So we only want 1 digit to represent up to 0 to 15. So instead of that, when we get to number 10, we're going to say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Instead of writing 10, we're going to write A to represent 10, B to represent 11, C to represent 12, D to represent 13, E to represent 14, and F to represent 15. So this is why we use these letters for hex. We're using this to represent numbers, right? So again, here F represents 15. So again, it's 0 to the base minus 1. And if you wanted to write 16 now, it's going to be 1 0. Why is that the case? Because this 0 represents the ones column. So the highest number of ones you can get, the highest number of ones is going to be 15. Anytime you want to write 16, you need to go in the 16th column right there, right? Okay, so I'll come back here. If we are coming here to convert or to expand, let's look at the hex example. Let's say we have F1, right? Again, F1 here, this is the ones column, so this is going to be 16 to the 0, and this is going to be 16 to the 1. Okay, F represents 15. So if we want to expand this, and again, anytime we say we're going to expand something, this is saying, okay, we're converting it back to decimal, right? Because the number we get is going to be a decimal representation. So again, if we expand this, what do we have? 16 times 1, this is going to be, so this is going to be 1 here. 1 plus what? Again, F represents 15, so it's going to be 15 times 16, right? So this is 16 to the 1. Anything to the 1 is the same thing. So again, 16 to the 1 is 16. So we have 16 times 15. And let me pull out my handy calculator right here. So this gives me 240 right here. So 240 plus 1, this is going to be 241. Right? So again, anytime we say we're expanding something, we are essentially converting it back to decimal. Now decimal is base 10, so you can write a small 10 at the back of it, so just we're not confused with anything, right? This is going to be hex, so we can also write a small 16 at the back of it, so we can know it's base 16. Likewise, we can write a small 10 here, so we know it's base 10. Let's come and do a binary example right here. So let's go 1 0 1 1 1 0, right? So again, this is going to be 2 to the 0, so this is the ones column, right? So I just put 1 right here. This is going to be the twos column. So this one is very easy. We don't have to write 2 to the 0 and whatnot. We just multiply by 2, right? So then this is going to be the twos column. This is going to be the fours column. This is going to be the 8th column. This is going to be the 16th column. This is going to be the 32s column, right? So now to expand this, how many ones do we have? 0 ones, right? How many twos? So we have 2 plus, so we just add up whatever, we have a 1 here. 2, how many 8s? Sorry, this is 4. How many 4s? We have 1 4. So it's going to be 2 because we have a 1 here. Plus 4 because we have a 1 here. Plus 8 because we have a 1 here. And we skip 16. We don't have a 1 here. So we go straight to 32. Plus 32. And this gives me, what is it? 10 here. This is 42. And then 4, 46. So this is 46. And we can write base 10 here, right? So you can see how we use the expansion method just to evaluate, okay, what is that number in decimal, right? So again, very easy for you to see. Now, there's one exercise that I put in the homework. I think it's in homework number 2. Something that you guys should practice. You should know because you need to memorize all these binary numbers. You need to write a table with decimal. You need to write a table with binary, octal, and hex, and you need to write the numbers from 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. You need to fill out this table, right, with all the binary numbers for these, with all the octal numbers for this, and all the hex numbers for this, because you need to memorize this table, right? What that does, it helps you to quickly realize the numbers that you're working with, right? So for example, for 0, if we just use 4 numbers, again, you can see here, as we go there, it's the same thing as adding 1, right? And of course, that takes us to the arithmetic that we do with the binary numbers. So 1 is going to be 0, 0, 0, 1. If you look at 2, again, we said anytime we write 2 in the base, it's going to be 1, 0. So 0, 0, 1, 0. 3, so again, this column represents 2s. This column represents 1. So 3 is going to be 1, 2, and 1, 1. If you look at here, so now we have 3 here. If you add a 1 here, you're going to have 1, 0, 1, 0, and eventually you have 1, 4, right? So you have a column to represent 4, so we put a 1 in the fourth column, and then 0 in the rest, right? So again, it's just like you get the overflow here. 1 plus 1 is 1, 0. So if you have 1 plus 1 here, you get 1, 0. And of course, that overflow or the carry will go over here, leaving you with 2 zeros right here. What about 5? 5 is going to be 1, 4, and 1, 1. So again, this is the ones column. 6, 1, 4, 1, 2, and 0, 1. 7, 1, 4, 1, 2, 1, 1. 8, 1, 8, and 0, 1, 0, 4, 0, 2, 0, 1. What about 9? 9 is going to be 1, 8, and 1 1. What about 10? 10 is going to be 1 8 and 1 2. What about 11? 1 8, 1 2 and 1 1. What about 12? 1 8, 1 4 and 2 zeros. What about 14? 1 8, 1 4 and 0 1. What about 14? 1 8, 1 4, 1 2 and 0 1. So what about 15? 15 again is the same as F. We have all ones here. What about 16? We need to have an extra digit for 16 now, because this 1 represents 8, right? Again, same thing for octal. Here, we're going to have 0 to 7, all the way to 7. Same thing here. When we get to 8, to write 8 in octal, it's going to be 0, 0, 1, 0, right? Because this represents 8 in octal. And when we will continue, 0, 0, 1, 1 for 9. Again, this represents 1, 8. This represents 1, 1. And then when we come down to 16, we're going to have 0, 0, 2, 0. Again, this 2 in octal represents 8. So we have 2 8s, which is 16. And then we have 0 1s. What about hex? I just showed you the hex on this side. It's going to be 0, 1, all the way down. Of course, when you get to 10, we're going to switch to A. And for 11, we're going to have B, C, D, E, F. And of course, when we get to 16, we're going to have 1, 0 to write 16 in base 16. So you need to complete this. I think this is part of the homework. Like I said, you need to memorize all of this so that when you see a number in binary, you can identify what it is. Even though you don't know, you can see, okay, well, what does this represent? This is the 1, so we have 1 here. Okay, we have, this represents 2, this is 4, this is 8. Okay, this is 8 here, 1 8 and 1 1, so this number must be 9, right? I think the other thing I shared with you is how you can convert between binary and octal, or binary and hex, because we said that for each hex digit, so if you have a hex here, for each hex digit, let's say we have 1 0 A, and this is base 16. We said if you want to convert from hex to binary, you need to have 4 binary digits for each hex digit. So you have 4 binary digit for each hex digit. So again, so for this A, we're going to write this A using 4 binary digits. So again, A is 10, so we're going to have 1 8 and then 0 4s, 1 2 and 0 1s. So we need to have 4 digits to represent this 0, 0 0 0 0, and 4 digits to represent 1 0 0 0 1. So this is the binary equivalent of this hex number right here, and you can go vice versa. So if I gave you a binary number, let's go 1 0 0 1 1 0 1 1 1, and I said convert it to hex, you just need to group it in 4s and then convert this 4 into 1 digit, right? So let's convert this 4 into decimal. This is the number 7 right here, so you just write this is 7, this is 1 4 1 2 1 1. This is going to be the number, this is 3 right here, so we have 1 2 1 1 1, so this is 3, and of course this is going to be 1, right? So this is 1. So this is going to be the hex equivalent for this binary number right here. Now for octal, you do the same thing, but you group it in groups of 3. So if you were to convert this to octal, instead of using 4 digits, you're going to essentially group it in groups of 3, right? So to go to hex to octal, you need to go through binary first, and then you go through you go back to octal. So again, let's do an example here. Let's say octal to binary, and say we have 1 7 3 and it's base 8. We need to convert each of this. So this is for hex only, hex, right? We need to convert each of these into 3 binary digits. So for 3, we're going to have 0 1 1. For 7, we're going to have 1 1 1. For 1, we're going to have 0 0 1. And this is the binary from this octal. And if you want to go back, the same thing. So again, let's have a binary number here. If you want to go to octal, we need to group them in groups of 3 and convert them to decimal. Okay, this 101 converts to 5. This 001 is 1, and then 1 is 1. So this is the octal representation for this binary number. How can you do it? You need to know this table, right? You need to be able to memorize this table so you can identify the digits, right? So when you see this, you know, okay, this is 6 and whatnot, right? That's how you can convert really quickly. Let's go on to the next thing I wanted to discuss quickly. So we talked about binary number systems and conversions. Next thing I want to discuss, probably I think I asked you about very in passing, 2's complement. So again, we talked about representing numbers in binary. We said, okay, we use the binary number system, right? In the computer, yes, we use binary, but then we also need to represent information, right? So for example, we need to represent, say, there are different numbers we want to represent. If you look at numbers, we have whole numbers like 7, 2, 1. We also have real numbers like 1.5, 0.002, and etc, etc. And then of course we have negative numbers, right? We have negative numbers, positive numbers. We need to represent them in binary. Now of course you'll learn more of this in the course as we proceed. There's different notations as to how we can represent binary numbers, negative binary numbers in the computer. One popular way that is used is we have the 1's complement and the 2's complement. Right, and of course with the 2's complement we are able to represent negative numbers, and we're able to do some arithmetic with them as well, that we will expose you to as well. So again, quickly, we said the 1's complement is the opposite. So if you have 0, 0, 1, 0, the 1's complement is just going to be the opposite of this. So 1, 0, 1, 1, 0, right? This is the 1's complement right here of this number right there. The 2's complement is this the 1's plus 1, right? So again, the 2's complement, normally we use it to represent a negative number. So we have 7 is going to be 0. Let's say we have 4 binary digits. It's going to be 0, 1, 1, 1. If you wanted to represent minus 7, right, it's going to be, you're going to take the 2's complement of this 7 right here, and it's going to be the 1's complement, 1, 0, 0, 0, which is the 1's, plus 1, and that gives you 1, 0, 0, 1. So this would represent minus 7, right? So this is the 2's complement right here. Okay, like I said, we will discuss it more as we continue. Let's jump into the logic gates. So again, so far I've said you need to memorize this table with all the different conversions. There's some other things that you need to memorize as well. We'll come into them now. Right, with the logic gates, okay, what is the logic gate? This is essentially a circuit. Inside of the circuit, you have transistors, right, that are used to design a circuit with particular states and with a particular logic under which it's going to operate, right? So because of the way the circuit is designed, it is only going to operate based on a particular set of instructions, right? So again, you guys discussed using transistors as a switch in your devices class. The circuits are very similar. Now we can go in and look at the circuit of each gate, but for the most part, this is not the focus of this class. We're simply using the circuit, right? And so we'll study, okay, how do we use it? What is the voltage that we put to it? What is the maximum speed, or what is the maximum frequency of a signal that we can use with this device? So we'll be definitely going to the data sheet of the devices to have a look at them, right? So again, the logic gate is a logic gates concept. They're also physical devices. So I brought some examples here just to show you before we go into them. Let's go back and put my screen back on so I can show it to you. All right, so on here, if you look here, for the most part, we have some ICs, and this is going to be ICs of logic gates, right? And the circuits that you expected to know how to build from this class is essentially using a breadboard. You'll be using this logic gates, using some resistors, and using some LEDs, right? You're probably using some buttons as well. So most of the circuits are going to be circuits where you design using maybe some push button inputs, and the output most times is an indicator so that we can see if the output is working, so you can verify the operation of the gate. All right. I know that these materials are available in the lab, so most of my examples are going to be using them, probably showing you how to connect the circuits as well. All right. So again, the purpose of the class, like I mentioned, is essentially to give you more practice. So we are saying that this class is not that difficult. The emphasis is so that you can get hands-on, you can use the circuits, you can design circuits, you can get more hours of practice. You can also be more confident in your fabrication skills as well. All right. So all of the gates that we're discussing, we have the model number. There is a data sheet for them. You can pull up the data sheet. In the data sheet, we have how to connect the circuit, so you don't have to guess at anything. You are basically using the resources that are given to you. What you need to know and understand is have a basic understanding of the gate, of the logic from that gate, of how you can connect it in a circuit, the loading and so forth. Now, of course, it's not difficult because the logic is in the name, right? For example, the AND gate tells you use AND logic, right? So let's go back here. I will just share with you probably something that I expect you to know, right? So building a circuit with them, not difficult at all, right? Piece of cake. Okay, so for the logic gate, what do we expect you to know, right? We expect you to memorize, right? You need to know it by heart because it will be on the exam. What do you need to know about all the gates? You need to know the logic. And I already said the logic is easy. Why is it easy? Because the logic is in the name, right? The name of the gate tells you the logic of the gate. You also need to know the symbol. All right, so you need to identify, okay, this is the AND gate, that's the name. Okay, if you see a symbol, you need to know that, okay, this is the AND symbol, right? You also need to know the boolean expression. So this expression also tells you that this is the AND gate, right? So we represent it using a logic, right? We represent it using a symbol, and we have a boolean expression because we can also do some arithmetic to tell us what to expect out of the circuit based on the inputs that are there. And then maybe I'll ask you for the K-map just to represent the truth table. So this is one way of representing the logic as well, right? The K-map represents the logic. Then we also have the truth table. And this truth table also represents the logic, right? So again, you need to know the logic for the gate, and we said the logic is easy, it's in the name, right? You need to know the symbol, very easy to memorize. Also, you need to know the expression, boolean expression. That one is very critical as well. You need to know the K-map and the truth table, right? Now, all of these things, like I said, just help to explain the logic. Why is this important? Because the gates are the basic building blocks of all the other complex devices that we're going to use later on in the course. For example, encoders, decoders, counters, timers. Logic gates are the basic building blocks, and we need to understand how the basic gates work so we can understand these complex systems, right? So again, what do you need to know with this? You need to memorize them. That is, you need to write them with your own hand. You need to study them, test yourself, quiz yourself until all of this information is in your brain. So let me go and just present you with the logic gates on the next pages. Let's start with the AND gate. And of course, for each gate, I'm going to give you all of these things. So again, if you pull up any textbook, you will find this information. Many videos online have the information as well. So it's not something that you have to figure out by yourself. It's been given to you. All right, so let's start with the AND gate. Okay, so the name is AND, and of course, we said the logic is in the name. This AND gate, if I were to give you the logic, the output is high. The output is high when both inputs are high. All right, so again, this is the logic for the AND gate. And again, it says the output is high when both inputs are high. Now keep in mind that we may have multiple inputs. We may have 1,000 inputs, for this gate. The logic happens, it's not just both, but when all the inputs are high. So if we have 3 inputs, all of the inputs must be high for the output to be high. That is the AND logic, right? This is the symbol for the AND gate. Now there are different ways of drawing the symbol. So I'm just going to draw one with 2. Probably I'll draw one with 3 as well, so you can see what we're talking about. So again, here most times we call this A and B, A, B, C, and then the output here. So this is the symbol for the gate, all right? Now you can write the output as Y, right? So again, so far we have the logic, we have the symbol. This is the symbol for the gate. Now, what is the Boolean expression that represents this, right? So the expression that represents this gate is going to be, we can say that Y is equal to A dot B. Again, so in writing the Boolean expression, multiplication represents AND. So anytime you see 2 inputs, and again the variable here is representing the input, and they are multiplied, it means that they are ANDed together. What about this one? This one is going to be Y is equal to A, B, C, right? Again, this says A ANDed with B ANDed with C. It tells us that all of this A, B, C must be high for the output to be high. That's what it says, right? Again, this is AND. The last thing we want to discuss is the truth table. So we already discussed the logic that says all the inputs must be high for the output to be high. We just have a table that represents this information. So the table captures this information here. Okay, so again, what do we have in the table? We have all possible combinations. So if we have 2 inputs, then we have only 4 possible combinations. So again, 0, 0, 0, 1, 1, 0, 1, 1. Of course, based on the logic we said, only when we have all the inputs high, which is only right here, this is where we're going to have the high output. Everything else should be 0, right? What about if we have the one of the 3 inputs? Okay, if with 3 inputs now, we have more possible combinations. It's going to be 2 to the n, so we're going to have 2 to the 3 combinations, which is going to be 8 combinations. So again, 8 possible combinations here. And again, based on the logic, the only time the output will be high is when all the inputs are high. Everything else is going to be 0, right? So this is the AND logic right here. The last thing, let's look at the truth table. If you were to write a truth table for this, again, the truth table is another way to represent the logic. So we can have here AB So again, here, most times here we have a 0 and a 1, 0 and a 1. All right, so again, in this truth table here, essentially what we're going to do, we're going to put a 1 in the cell that represents the output, right? So again, in this case here, A0, B0. Here, A0, B is 1. Here, A0, B0, A is 1 here, B0. But in this case here, see here, A is 1 and B is also 1 here. So the 1 goes here. So the output is 1 only here. Of course, all of here, we can put 0 here. We can choose to put 0 or we can choose to leave it blank. It's up to us, right? So this is the logic for the AND gate, right? Then, of course, you know that we have the OR and we have the NOR. I noticed our time has come to an end. Just to end, I'm going to probably go ahead and just complete the gates, and I'll end here. So if you had to, I said that we would end at 6:45. So if you have to leave at this time, that's fine. But I'm just going to complete the gates. Like I said, all of this here on this page, you need to memorize this, right? Because it will really help you going forward. Okay, so let's go on to the next gate. Again, keep in mind the AND gate, right? And just keep the logic in mind. It helps you later on because we'll come back to this when we do the NAND gate. Very quickly, we come back to the next gate that we'll look at is the OR gate. Now, if we look at the logic for the OR, this logic, we said the logic is in the name. So this output is high if any output of, or if any input is high. In other words, the only time this is going to be, the output is going to be low is when all the inputs are low, right? So again, if any input is high, the output is going to be high, right? So this is the logic here. It's called OR logic, right? So if you were to have the symbol for the OR gate, this is the symbol for the OR gate. I'm going to draw one with 2. And I'm also going to draw one with 3 as well. Okay, so again here, this is the symbol for the OR gate. The next thing you need to know, you need to memorize, is the Boolean expression for the OR gate. Again, it's going to be y is equal to a plus b. Again, this plus here represents OR. Anytime you see this plus, it represents OR. Likewise here, it's going to be y is equal to a plus b plus c. Likewise, the truth table. Again, how do you represent? Another way of representing the logic is with a truth table. So we'll write it here, a, b, and y. Like we said, okay, here we have all the possible combinations of the inputs. And again, here in our truth table, the output is going to be high anytime we have a high input. So here, anytime the input is high, the output is high. So the only time our output is low is when we have all inputs being low. And likewise for the one with the 3 inputs, we're going to have 8 possible combinations. And this possible combinations is essentially counting to 8. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right, just counting to 8. And of course, the only time we're going to have a low for the input is when we have all the inputs are low. So we're going to put the 0 right here for the low, and everything else is going to be high. All right, so this is the OR logic, right? Let's go on and talk about the inverter logic, right? So what is an inverter? We have a NOT gate or an inverter. So as the name suggests, the output is the opposite of the input, right? Output is opposite of input. And this is the symbol that we use to represent the inverter, right? So if A is, we have A here and we have Y here, right? So again, if you were to describe the logic here in a truth table, we can say that A is going to be the opposite of, so Y is going to be the opposite of A. So if A is 0, Y is 1. And if A is 1, Y is 0, right? Again, that's because Y is the opposite of A, right? So sometimes we don't use the whole gate, we just use a bubble, right? So there's a truth table for it. I think I forgot the K-map for the other one, but that's okay. Okay, so now we can go into some other gates. Again, so far we look at the AND, we look at the OR, and now we're looking at the NOR. We're saying it's just an inverter. So one application of the inverter, we talked about the ones complement. So just imagine if you have some digits here, 1, 0, 1, 1, and you wanted the ones complement, you can pass it through an inverter, and you will get the ones complement at the end of the inverter. Because the inverter will give you the opposite of the input. So again, if your input is 1, you're going to have a 0 here. Your input is 1, you have a 0. Your input is 0, you have a 1. Your input is 1, you're going to have a 0. So this is the ones complement. So this is the application of the inverter. Let's go on to the other gate that you need to memorize. This one is called the NAND, right? Again, like we said, we're saying that the logic is in the name. So this is saying it is the opposite of the AND, right? So again, how does the NAND work? It's going to be the opposite of the AND. So if you were to describe it, the AND says when all inputs are high, the output is high. Again, this is the opposite of the AND. So it's going to be saying when all inputs are high, output is low, right? So output is low because it's just the opposite of the AND. when all inputs are high. So what's the symbol for it? It's the same as the AND, but we're going to have an inverter on the back of it just to invert the output. Same thing here. So another way of drawing this is simply to draw a AND, and you draw a NAND, sorry, an inverter on the back of it. Right? So this is exactly what the NAND is, right? It is an AND, but the output is inverted. All right, so let's write the logic for this. How do you write the Boolean logic? We say it's the same thing. A and B, the dot represents and we put a bar over it to represent we put a bar over it to represent that it is inverted, right? Likewise here, same thing here. So if you wanted to write the logic at the different stages, the output of the AND is going to be A dot B. And when it goes through the inverter, it becomes A dot B bar, right? So anything that goes through the inverter, it comes out with the bar on top of everything, right? Let's go ahead and write the truth table to represent this NAND, all right? Again, it's going to be very similar to the one we had. The only difference is that instead of the output is going to be inverted. So let's look at our output. So we have same thing here, 0, 0, 0, 1, 1, 0, 1, 1. So if we have a 0 here, we're going to have a 1 here, right? Because we have an inverter right here. If we had a 0, we're going to have a 1. If we had a 0, we're going to have a 1. And then we have a 0 for our, when we have both inputs high, the output is now inverted, right? Again, if we had a truth table with 3 inputs, it's going to be very similar, right? We expected to have all ones here, and then for 0, 0, we're gonna have, sorry, for 1, 1, we're gonna have a 0 right here. Let's do the K map for this one. So again, if we use A and B here, and 0 and 1, 0 and 1, of course we expect everything to be 1 except for 1, 1, which is gonna be 0. Right? Again, 1, 1 in all the different combinations. Only when we have A and B both being high, we're gonna have a 0. Let's go ahead and do the OR gate. Let's do so we have, so far we have the AND gate, we have the OR gate, we have the NAND gate, we have the inverter as well. We'll go ahead and do the NOR gate. Right now, the NOR, the logic is in the name. So again, the output is high. Again, just look at this here. If we invert this here, right, then this 1 becomes this 0 becomes a 1. This 1 becomes a 0, 0, 0. So the output is going to be high when both inputs are 0, right? Output is high when both inputs are 0, right? So you can see here what the symbol for the NAND is going to be. Sorry, the NOR. Again, it's the same symbol for the OR. We just add a bubble at the back of it. The bubble represents the inverter. So we can write the expression as y is equal to, again, for OR, we use the plus, A plus B, but we put the bar on top of everything, right? So again, we can also write it this way. So you can see that is really an OR gate with an inverter. All right, so again here, the expression will be A plus B here. After it goes through the inverter, it becomes A plus B bar. All right, so again, same thing right there. If we add another input, let's add C right there. It's going to be A plus B plus C, A plus B plus C, and again, the bar is on top of everything. Of course, we're going to have, if we look at the truth table, if you complete the truth table, we're going to have a 1 up here and everything else will be zeros right there. Y is going to be equal to A plus B plus C, all bar. All right, so let's do let's go ahead and do the K map for this one and the truth table as well. Again, this truth table is the opposite of this because the output is inverted. All right. Let's do the K map as well. The only time we have a 1 is 0, 0. Everything else should be 0. All right. So again, we did the AND, we did the OR, we did the NAND, we did the NOR. We still have 2 more to go. And of course, we talked about the inverter. We have 2 gates that are really special. The first one is called the EXOR, or we call it exclusive OR. And so the logic for this gate is that when the inputs are, only the output is high, when the inputs are different. So when we have different inputs. Okay, what does that mean? Okay, here's the symbol for this gate. It looks like the OR, but notice it's special in the way it is. Right, it's the XOR OR. Again, the expression for it is A plus B. And again, this plus has a circle. So this is the XOR OR. Another way you can write it is AB bar plus A bar B. Right? Okay, so then we come to the truth table. Again, we said the output is going to be high when the inputs are different. So if we have A and B, when the inputs are different, so the inputs are different here, 0 and 1 here. So the inputs are the same, we have a 0. The inputs are the same here, we have a 0. So again, you can see here that this output is only high when the inputs are different, right? Again, we use this gates for some special applications. We have the opposite of it, which is also called the exclusive NOR. And of course, the exclusive NOR is the same as the exclusive OR. The only thing is that we have an inverter on the back of it. So just expect that the output will be inverted. So how do we write the expression? Y is equal to A plus B. Again, this inverter here just means the bar across everything. And yes, if you want to write this way as well, it's going to be A, B bar plus A bar, B all bar. Again, when you put the bubble, it's bar across everything. The truth table, we expect it to be the opposite of this one right here. So we have 0, 0, 0, 1, 1, 0, 1, 1. And of course, we expect to have a 1 here where we have it the same, and a 1 here where we have it the same. Right? So this is the exclusive NOR. Now we will use the Boolean algebra and Boolean algebra simplification to simplify this expression later on. Right? So this is essentially going to be the next part that we'll discuss, using Boolean algebra and doing Boolean simplification. Right, so again, these are the gates that we discussed today. We had the NAND, the AND, we had the NOR, the OR, and the inverter as well. So like I said, you need to know for each of these, what is the logic. Then of course, you need to know the symbol. You also then need to be able to you need to know the Boolean expression for it. Again, we said plus represents OR, and multiplication represents AND. And then you need to know how to express the logic in the truth table. So again, this is the output is high when any input is high. So the truth table should show that anytime we have a high input, we have a high output, and vice versa. Right? So let me just show you an example of what you should be able to do, and what this exercise will help you to be able to do before we end. This is the last thing we're going to discuss. Right? So knowing that plus represents OR and multiplication represents AND, if I give you some expressions, you should be able to draw a circuit representing them. So for example, let's start with an easy one. Let's say A plus B plus C bar. Right? Now, we said the bar is as a result of an inverter. So you will see that the bar can come on the input or on the output, right? So this multiplication here tells us it's an AND gate. So this is going to be an AND gate, right? So the output of the expression is going to be A, B, C bar, right? So for A goes in, for B goes in, and for the input here, instead of having C directly, we can have C bar here, or we can decide to have C and then draw a small bubble here to represent the bar, right? So again, if you know that this is AND, you can draw an AND gate like this, okay? Let's go to the next one. How about we have A plus B plus C plus D bar, all right? So again, we know that this is the OR gate. All of this is OR. Plus represents OR, so we draw the symbol for the OR gate, and we just put the inputs A, B, C. Like I was saying before, if you don't want to draw C bar here, we can decide to just put D, and we put a bubble here representing an inverter here. So like after the bubble, we're gonna have D bar. So D bar is what is going to go inside of here, and the expression at the output we get is A plus B plus C plus D bar, right? Eventually we'll be able to combine this, right? We'll be able to combine them. So for example, in this one, the one we saw for the exclusive OR, it was A B bar plus A bar B. So again here you can see that we have a combination of the AND gates and a combination of the OR gates as well. So the way you do that, you just take it one step at a time. So let's do the first one here. This is the AND gate. The multiplication represents AND, and of course the B term is inverted. So we can say that this is going to be A, and let's say this is B, and let's put a bubble here to represent an inverted. So this is A B bar coming out of this, A B bar. Again, the multiplication represents an AND, and then we see another AND gate here, and the inputs for it is A bar. So let's take A from here, come down here, and let's put a bubble here to represent the bar. And then let's connect B to this guy, right? So this is going to be, so the output of this is A bar multiplied by B. And of course you see that they are plus together. Plus represents OR, so we draw an OR gate, and the inputs for the OR gate is going to be this guy here and this guy here. So the output of the OR gate is going to be A B bar ORed with A bar B. So again, eventually this is what we're going to do. We're going to use expressions and draw the circuit, and of course we can do it vice versa as well, right? So let's do a vice versa quickly. We have a circuit here, all right. So we will write the expression for this, right? So let's say A, B, C. Maybe we'll put B down here as well. This is B, D, and let's say this is A bar here. Okay, so we are given a circuit. We are told write the expression for both outputs. So this circuit has multiple outputs, right? So again, what is the expression for this right here? Then we can see, okay, well, this is the AND gate. Let's put a bubble here. So let's just mix things up a bit. So what is the expression for this gate here? So what are the inputs? So the first input is B. So this is going to be B, and it's AND, so it's a multiplication. B D, right? So this is the expression for this gate. What is the expression for this gate right here? It's going to be A and B bar, because you have a bubble right here. A ANDed or multiplied by B bar, then this is here we have C. Now because we have a bubble at the back of this AND gate here, we're going to put a bar on top of everything. So then we go to this gate right here. What are the inputs of this gate? So this is the OR gate here, and this input is inverted. So the input for this is going to be A B bar C all barred, ORed with, again, plus represents OR. Plus if we're ORed with what? With A bar plus A bar, right? So this is the expression for this one, for this output right here, right? Now, what is the expression for this one? So we see BD ANDed with something else. ANDed with what? This entire expression here. ANDed with A B bar C plus A bar. Of course, we put a parenthesis around it just so we can know it's a separate term. Again, same math rules apply. So again, we have come to the end of the session for today. Like I said, I look forward to the other session that we're going to have, where we're going to go into some Boolean algebra. We're going to do some simplifications. Like I said, we're just speeding through the material. If you have any questions, stop, and I will definitely explain everything. Thank you so much.